Achieving a pulverized coal injection rate of 250 kg per THM is often called the impossible frontier in iron making. For 20 years, we have hit a wall at 180, but today we are going to break that ceiling. By the end of this session, you will get three critical deliverables. First, a deep understanding of the re-engineered aerodynamic requirement for ultra-high PCI. Second, the mathematical proof that oxygen stoichiometry, not just volume, is the heartbeat of the furnace stability. And third, a blueprint for the body and chemistry that prevent lower furnace blockage. So on your screen, you see a glowing 3D wireframe blueprint of the target furnace with the data stream flowing towards the future. So this is not just a schematic, it's our mission map. To reach this height, we have to address the fundamental crisis that occurs when we push past current legacy limit. So let's look at the actual data gap between our current stability and the high pressure reality of 200 plus rate. So coming to our next slide, which is about uh, re-engineering aerodynamics. So the crisis is simple. Pushing PCI beyond 180 kilogram destroy efficiency unless internal aerodynamics are completely re-engineered. So look at the visual on the left. You see smooth electronic blue airflow lines entering the furnace at 150 kilogram. But look at what happens at right when we push 200. Those lines turn into chaotic neon coral mess of turbulence. Notice the data sketch at the bottom. At 150 kilogram, we expect and achieve a stable fuel rate of 480. But at 200 plus, while we expect a lower fuel rate of 450, the actual rate spiked to over 500. So that is a system warning. This means the furnace has moved into high pressure state where your coke is no longer just fuel, it's being crushed. The so-called here is clear. If you don't re-engineer the flow, you are not saving money. You are actually burning more fuel to fight your own furnace pressure. So to solve this, we had to move beyond surface level observation and map the invisible zones of the furnace. So as you can see, this about the mapping the invisible. So we cannot fix what we can see. To build this strategy, we combine the live sensor telemetry with the post-mortem furnace dissection to map the invisible combustion zone. So look at the 3D cutway. Those glowing things are getting connected by the green arcs represented by the data points from our twin probes and the CFD velocity mapping. So the table in the corner shows our resolutions. We are pulling gas analytics every 10 millisecond. Why? Because at 250 kilogram of injection, the kinetics happen so fast that 1 second delay in data is an is a big cause. So we also conducted dissection study measuring microscopic deadman of char at concentrations of 10 to 4th power per kilogram. So this marries the black box machine data with the physical forensic evidence from inside the hearth. This level of resolution allows us to identify the specific oxygen ratio where the furnace begin to suffocate, and that suffocation point is defined by a single critical variable, the oxygen stoichiometry ratio. So coming to our top insight number one is which is about the oxygen ratio. So oxygen threshold here is the most critical technical finding of our research. So look at this radiant green curve which represents the furnace permeability. So everything is stable until you hit an oxygen ratio. So denoted as a mu of zero point 0.7. The moment you cross that red vertical line, the curve drop of a cliff. So follow the neon coral line as it descend into the critical choke point. The data sketch reveals the brutal reality. At a mu of 0.85, the furnace is flowing perfectly. At zero point 0.7, unburnt char volume increases by 15%, but at 0.67, char volume explode by 300%. So what factor here is operational survival. If your oxygen stoichiometry drops below zero point 0.7, unburnt char will aggressively suffocate your furnace permeability, leading to massive char formation and eventual hanging. We must maintain that stable green zone at all costs. But char is not the only threat. We also have to look at how high injection rates change the way structure of the coke. So coming to the same thing through the top insight number 2. So as you can see, the coke structure paradox. This is a paradoxical finding that many managers misses. So as we increases the PCI, we lower the overall coke rate. You would think that that's good, but it's artificially concentrate aggressive chemical attack on the remaining coke structure. So look at the split screen macro photography. On the left, you see the healthy thick walled coke slit of a low PCI operation. On the right, at 200 kg, you see the magnetic crack of a structural failure. The data table tells the story. Solution loss per coke increases by 22%. Because there is a less coke, each remaining piece takes a higher chemical load. Deadman finds smaller than the 3 millimeters increase by 300%. The operational impact, your load bearing coke is becoming glass. It's a shattering before it even reaches the hearth, which destroy the voidage needed for the gas and the liquid flow. So if the coke is failing, we must look the other half of our burden, the center, to provide the relief. And this is a very good proposal. So top inside 3, as you can see, the purity threshold. So we have found a mere zero point 0.5 reduction in center silica dictate whether the lower furnace breathe or block. So look at the optimized bar on your screen. By dropping silica from 5 to 4.5 only, the permeability index or Ks drop from a high resistance 1500 to a high flow 700. So this is a massive 50% improvement in the gas flow for a teeny chemistry change. So the magnifying glass visual shows the microscopic structure. Lower silica means less slag volume in the cohesive zone. The so what here is pure economics, saving pennies on the uh, uh, cheaper and high silica ore is actually costing you millions in the lost productivity because the furnace cannot breathe at higher injection rate. So you must purify the center to compensate for a higher char loading. We are expecting at 250 kilogram front here. So to manage this material effectively, we have to understand exactly where these reactions are taking place within the furnace zones. So coming to the deep dive 1, which talk about the 3-step combustion path. So let's apply the process structure properly, and property framework also to be studied to combustion path. So there are 3 distinct zones here. First, the blowpipe shown in the electric blue, where the devolatilization occur. So these changes particle porosity and determine the combustibility. Second, the raceway in amber yellow, where the C plus O2 reaction create our thermal output and heat flux. Finally, the cohesive zone is in magneta. So this is where the danger lies. If unburnt char escapes the raceway, it chemically attacks the ore layer, fatally restructuring the cohesive zone. The table shows the output. If you have a slag blockage, your melt down temperature shift, leading to a slag blockage boarding. The so what is that? Damage start at the grain boundary of the ore, not the surface. If you don't control the reaction kinetics in the blowpipe, you ruin the property of the cohesive zone. This damage becomes more pronounced as we push the limits, because the efficiency of coal replacing coke is not a straight line. So deep dive 2. So diminishing replacement ratio, we need to talk about the law of diminishing returns in PCI. So look at above 150 kilogram, every additional injected kilos replace progressively less structural coke. So look at this animated step flowchart. At the rate below 100 kilogram, the replacement ratio is near ideal 0.95 to 1.0. At our 150 kilogram baseline, it is 0.85. But look at the drop off. Above 190 kilogram, the ratio falls below zero point 0.7. Why? Because the excess air ratio is no longer ideal, and we are generating more char than we are burning coal. So operational impact is a massive hidden cost. If you are injecting 200 but only replacing 140 kilogram of coke, your total fuel rate is actually skyrocketing. You are spending money on the coal and oxygen just to create debris that block your furnace. So when that debris accumulate, we see high furnace pressure, but we need to understand the root cause of that blockage. So root cause analysis, the debris staircase, as you can see. Uh, so when you see the high furnace pressure, don't assume it is an air volume issue. It's a micro structural debris blockage. So let's walk down to the 5 whys staircase. So why do we have high pressure? Because gas resistance in the lower zone is too high. So coming to the other part, so because gas resistance in the lower zone is too high, why? Because the voidage is filled with the fine debris. This is the basically cause. So because the dead man coke has settled into -3 millimeter fines, why did it settle? Because of the concentrated solution loss. So the root cause is chemical attack on the coke structure, not the blast volume. So look at the data evidence. Solution loss is the fire that burns your structural support. And the so what is that increasing blast pressure to force air through just make the problem worse by further crushing the weakened coke. So to prevent this descent down the staircase, we must map our safe operating window using a phase diagram. So the operational map, that is safe versus danger, as we can see in the next slide. So this is your operating map for the ship. Keep the needle on the left side of this line. In the emerald green zone where mu is greater than zero point 0.8, you have optimal flow. As you move into the amber, the transition zone between zero point 0.7 and 0.79, you must immediately enrich your oxygen. If you hit the neon coral zone where mu is less than 0.67, you are facing a system collapse. The table is your action plan. Cut PCI immediately. Do not wait for a meeting. If the stoichiometry hits 0.67, your furnace is already choking on char. The so what here is real-time asset protection. This map allows you operators to make high-stack decision based on the mathematical threshold rather than gut feeling. So staying in that green zone require a mathematical balance between the oxygen and our physical injection hardware. So coming to the our web of influence, so which shows a good correction matrix where furnace stability is not a single lock, it's a web of influence. So look at the central nodes of the furnace stability. They are mathematically bound to particle dispersion and structural survival. We found a strong positive correlation and an R value of 0.92 between using a double lance and a improved cold dispersion. So similarly, oxygen enrichment has an 0.88 correlation with maintaining the correct flame temperature. However, look at the strong negative correlation of 0.85 between high PCR and coke fines. So the operational impact is that you cannot increase one variable in vacuum. If you increase PCR, you must increase oxygen and upgrade your lance design simultaneously to maintain the equilibrium. If you do not, the negative correlation will pull your furnace into instability. So let's look at the specific hardware upgrade that makes the 0.92 correlation possible. The eccentric double lance. Coming to the advanced injection technologies, and which is also very important slide. So as you can see, the advantage looks at the split stream flow visual. So the top half shows a single axial lance. Notice the feeling flow and the narrow red stream of the coal. It results in a 300 degrees Celsius gas temperature drop and only 60% burnout. So now look at the advanced double eccentric lance. By the injecting at an angle, we create optimal dispersion in glowing green. The temperature drop is only 100 degree and burnout jumps to over 75%. So by improving volatile dispersion and ignition rate within the blowpipe, we drastically reduce char output. The so what factor is that this hardware upgrade is the enabler for 250 kilogram frontier. It ensures the coal is a gas before it ever touches the coke. So while we fix the coal injection, we also need a strategy to protect the coke that remains. So coming to our burden strategy is about this mix a small coke and as it shows a very detailed view. And our second major enabler in this slide is a burden strategy change. So on the left, standard layering is a stagnant. The primary load bearing coke is exposed to all chemical attack as all know. So on the right, we have mixed 50% small, highly reactive coke into the ore layer. Look at the glowing green arc. These small coke act sacrificingly, so it aids the solution loss and char, preserving the large coke-bearing coke in the center. The data sketch shows the benefit reduction time drops from 240 minutes to 180 minutes. The operational impact is profound. You are using cheap small coke to protect your expensive structural coke. This keeps the furnace breathable even at extreme injection rate. So when we combine these lances, the enriched blast and the mixed burden, the target becomes achievable. So coming to the our next slide, which is about the forecast, that is about breaking the legacy limit. So as you can see, here is our forecast trend line. So for decades, the industry has lived under the legacy limit of 180 kg, shown by the flat blue line. Our current unoptimized state often result in a replacement ratio below 0.7. But look at the amber dotted line breaking through. With the oxygen enrichment, we hit 200 kg with the frontier architecture combining double lance and mixed burden of 250 kg becomes mathematically viable with a replacement ratio of 0.85 or higher. Look, so this is not a dream, is a forecast based on the data we have reviewed today. The so what is the future of your plant's competitiveness. So this is how we reduce hot metal cost and extend the life of our assets. So to close its, let's summarize the three pillars you must implement to conquer this ceiling. So the three pillars of the frontier are like this. We have covered a lot of ground. To conquer the PCI ceiling, you must stand on these three pillars. So pillar 1, blast control. Maintain oxygen stoichiometry above 0.75. Pillar 2, lance upgrade. Switch to double eccentric injectors to ensure over 75% burnout. Pillar 3, burden chemistry. Purify your sinter to low silica levels and implement mixed small coke to keep deadman fines below 15%. Follow these steps and reach the blast. Upgrade the lance. Purify the sinter. If you do this, the 250 kilogram frontier is not a number. It's your new standard operating reality.